Hey guys, welcome to my first video, and today we'll be trying to build some intuition for this very powerful tool called the Cauchy product. In this case, we're gonna talk about the infinite sum version. So what we have here is the sum, as I is going from 0 to infinity, of this sequence a sub I, multiplied with a similar infinite sum but with this sequence b sub I. This product is equal to the infinite sum as n is going from 0 to infinity of the sum as k is going from 0 to n, so the n here is being used here, of this product a sub k times b sub n minus k. So how do we even begin? The idea of this tool is to expand this product of sums with many terms. So we can begin with the most simple but at least non-trivial case. So here we're gonna deal with finite sums first, like a plus b times c plus d. How do we approach this? Of course, it's a very standard result. We learned this very early on in algebra. So what we're taught to do is we're taught to draw lines like this and match one term from the first sum to one term from the second sum, and from there we get four different terms: AC plus AD plus BC plus BD. So two things we want to take note of when we're doing this expansion is we don't want to double count. Or count terms that shouldn't work, like a times b. That makes no sense. You should only get AC, AD, and BC, BD. And another thing we should take note of when we expand is we want to get every single possible combination. And what that means is each term from the first sum must match with every term in the second sum exactly once. And likewise for the second sum, every term in the second sum must match with every term in the first sum exactly once. Yes. So this process will become more complicated if we consider bigger products like a plus b plus c times g plus f plus why did I do it backwards? G plus f plus d, e plus d plus c. What am I doing? Yeah, so over here we expect to get 15 different terms, and that's a lot of lines you have to draw if we're gonna draw it, like try to match all the terms from the first sum with all the terms from the second sum. This is especially more difficult when we have more and more terms, especially when we go up to an infinite number of terms. So maybe we are gonna try and visualize this a different way. We can start off with writing out sums in like a parallel fashion, so something like a0 plus a1 plus a2 plus a3 plus and so on we have b0 plus b1 plus b2 plus b3, writing them like this. And now at least we aren't drawing curves, we're drawing straight lines like this. We're trying to match a0 to all the b terms and a1 to all the b terms. And using this process, we will get the expansion. But an even better way to look at this is if we flip this sum horizontally. So this is what I've made, and this is the A series in the usual ascending order, well, at least ascending indices. And here we have instead descending indices for the B series. So what kind of an algorithm, or how should we get all the terms in the expansion? So first we can start with this. So we have maybe we'll call this S first, and we have S equals, first we want to match the 0th term from each, and we get this A0 B0, and then afterwards we're gonna match the first two terms with the first two terms from each series. So here we have A0 and B1 and A1 and B0. I'm gonna write in a new line here, A0 B1 plus A1 B0, and here we're gonna match the first tree with the first tree. So we have A0 B2 plus A1 plus A0, and we can repeat this process. So we have A0 B3 plus A2 plus A2 plus A3 B0 and A0. So this is a pretty interesting perspective on how to expand the product of two infinite sums, and there's a pretty clean way to express all of this. So how should we rewrite A0 B0? We can rewrite A0 B0 as the sum, as k is going from 0 to 0 of A sub k times B sub 0 minus k. If we check, well, k equals 0 is the only term here. So we have, if you sub in k equals 0, we have A sub 0 times B sub 0 minus 0, which is 0, and we get back this A0 B0. And next we have this another sum. You can write this as k equals 0 to 1 for the rising index for the A terms of AK sub. In this case, we have a descending index for the B component. So we can write it as 1 minus k, where, let's just check, if we sum in k equals 0, we get A0 B1, which is here, and if we sum in k equals 1, we get A1 B0, which is here. And you can check, but the rest will also have a similar structure. So we have k going from 0 to 2 of A sub k times B sub 2 minus k. And the next is, we can clean this up even more. Well, okay, maybe I should start with the product, this S, which is the product of two sums. Maybe I should have called it P instead, but it's fine. this s is equal to the sum as I from 0 from 0 to the of a line of negative the sum as I from 0 to the of b line. This is equal to, let's see, there's a obvious pattern here. We have 0 here, and we have 1 here, we have 2 here, and 3 here. So we can write this as, we can call the variable n going from 0 to infinity of the sum as k is going from 0 to, well, n of a sub k times b sub n, the n here, minus k. And this is the Cauchy product. And this is just a way to visualize how the Cauchy product comes about. You can look up the finite series version, but it's only slightly more complicated because over here we need to be careful about what bounds of summation we're using here. But otherwise it's not too bad. Maybe we'll check the process we took again, just to make sure that these two conditions are met. So let us start with this. And maybe a good way to check this is to follow A0 and check which B terms it has been matched with. So first here, A0 is matched with B0. In the second iteration, we have A0 matched with B1, and then after that, A0 matched with B2, then after that, A0 matched with B3, and after that, A0 matched with B4, and so on and so forth, all the way up. So here we can see that actually A0 matches with every single B term exactly once, and that's exactly what we want. And now we can follow A1, and we can see that, well, over here A1 doesn't match with anything. Here A1 matches with B0, here A1 matches with B1, and so on and so forth. Again, by the same logic, A1 matches with every single B term exactly once. And the same can be said for every term in the A series. By kind of symmetry, you can say the same for every term in the B sequence. So here, we don't double count, and we do get every combination, so we're good to go there. That's just a gut check to make sure that our algorithm is correct. And this process of having two sequences, having one flipped horizontally and then matching terms and having this sliding action going on, is what we call a convolution, the convolution of these two sequences. The Cauchy product can be used in tandem with Maclaurin series expansion. So suppose we consider two functions f and g, and Maclaurin series expansion. So it's standard that this f of x equals to the sum as I is going from 0 to infinity of the ith derivative of f evaluated at 0 divided by I factorial, and this is multiplied by x to the I. But we're gonna Notice that this is a constant, not inclusive of the x to the I part. And we'll rename it as, well, we can call it a sub I, it's fine. And likewise, we'll call g of x to be equal to the sum as I is equal to 0 of b sub I x I. For us to use the Cauchy product, we have to have a product. So maybe we can think about the product of these two functions. And we will have the sum as I equals 0 of a sub I x I multiplied with the sum as I equals 0 of b sub I x I. And we have a tool for this, and it's called the Cauchy product, as you probably have guessed. If we bring this in to help us out here, we have the sum is the sum multiplied by the sum is this double sum, so we can do the direct substitution. So we have this sum as n equals 0 to infinity of the sum as a equals 0 to n of. Here we're going to replace a sub I with a sub I times x to the I. So in this language, we're going to have a sub k times x to the k. And for this, we're going to replace b sub I with b sub I times x to the I. And what we end up with is times b sub n minus k times x to the n minus k. And we can clean things up a little bit. We can have the sum as n is equal to 0 to infinity of the sum as k is equal to 0 to n of. Maybe we'll bring the constants out forward, and we have a sub k times b sub n minus k. And then after that, we have x to the k times x to the n minus k. The exponents will add up, and we have n minus k plus k, which is n, times x to the n. And since this part, this x to the n part, doesn't depend on this k, we can bring this out of the sum. And this is a pretty cool result, because here we can call this c sub n, where this c sub n is a sequence, another sequence. And we don't have a k here because this k is a dummy variable. And we get the sum of c sub n x n. What we ended up with is the Maclaurin series expansion of f of x times g of x, which is pretty cool. We have exactly the same structure as what we had just now. We have the relationship between the Cn and these two coefficients here used here. In essence, we were able to get from the product of two functions which were each expressed as their Maclaurin series and end up with a Maclaurin series. We can visualize this slightly more easily with again this sliding array of powers of x here. So here we have f, and this is g. F of x equals to this sum, and g of x equals to this sum. And here we're doing the product, and this is kind of the process that we're taking. First is a sub 0 times b sub 0. By multiplying a sub 0 with b sub 0, we get the constant term. And if we slide it once, we have this. If we multiply these two and multiply these two and sum them, we get the x terms. So here is all the information you need for getting the x terms, the linear terms. And here, again, is all the information you need to get the x squared terms. Here we get the x squared term, because x squared times constant term is constant, is a quadratic term. Here you get a quadratic term too, you get a quadratic term here too, and so on and so forth. You get a cubic term like this, you get the quartic term like this. And that's how you know exactly what the coefficients of each powers of x is. So for example, the quadratic term, if you get try and find the coefficients of the coefficient of the x squared term, we'll just have to look at this, and we can see that it's a0 times b2 plus a1 times b1 plus a2 times b0. And that's exactly what Cn is if we sub in n equals 2. And the same can be said for every other term in this sum. So here we're hiding a lot of information about what exactly is the relationship between ak and bk, b sub n minus k and Cn, and what's the significance of this. So here we can do a little bit of exploration. So let's look at this Cn. Since Cn is actually the coefficients of the powers of x in the Maclaurin series expansion for f times g, we can write it like this. The nth derivative of f times g evaluated as 0 divided by n factorial. And here we also declare that ai equals to the I derivative of f divided by I factorial, and b I is equal to the same thing, but instead of g. This is just what we get from Maclaurin series expansion. And this means that, let's see, Cn equals to, let's see, let's draw an arrow. Cn equals to the sum, as k is going from 0 to n. Over here we know what Cn is in terms of aka and the A sequence and B sequence. So what's ak? Ak is nothing but the kth derivative of f evaluated as 0 divided by k factorial. And we multiply that with b sub n minus k, which is the n minus kth derivative of g evaluated as 0 divided by n minus k factorial. And this is also equal to this. Just carrying it over. So here we can multiply n factorial on both sides, and we will have n factorial divided by k factorial times n minus k factorial. And that's precisely n choose k. So if we bring n factorial over to the other side, we will have this quotient, and we'll get n choose k. Then what's left is all this. Just bring it on. This is a pretty interesting result that we have come across. It's something that we might make a video of in the future, but in this form it's probably a little bit difficult to unpack. A further fact is, if we thought instead about Taylor series expansion, so a generalization of the Maclaurin series where we don't necessarily have to center the series expansion at 0, but you get to choose to center it at any real number. We actually get that if we follow all the same steps, that we don't, 0 is not a special number here. We can have any t. And I think that's a pretty cool result. This is actually a generalized version of the product rule of differentiation. So instead of differentiating just once, here we can differentiate a function as many times as we want, and we will have a formula for it. But this, we can talk about this another day. Hope you guys enjoyed this video about the Cauchy product. We took a little bit of a side tangent here in this interesting discovery. But that's all for the video.